Okay, just want to confirm again, you guys are looking at my screen and everything is okay, loud and clear? Great, thanks. Okay, let's start. Uh, Now DFT is a okay. Move the teams out of the way. DFT is a interesting chapter. It is a chapter that uses linear algebra to understand Fourier transform for our part. There's a lot to learn, but all the slides are here. And if you need references and examples, you can go to page 25 of 8A.3, and then you can see all the how other universities have taught DFT, or some of the universities. They are very good references. And I also give you links for visualizations and examples of working like what we have to do for our tutorials. So there are also additional stuff for things that you might have interest in. Now let's begin. What is the problem we want to solve? And I want to show it to you in a different way, different to the recordings I have done. So let's skip all this first and immediately go to what DFT is, or what Fourier transform is. So I'm going to open up this slide so that I can write. Right, let's motivate what is Fourier transform first. And Fourier transform basically takes in an input signal. So let's input signal. And let's not care about what kind of representation it is. In this example, it is a continuous time representation. We're just trying to make you understand what Fourier transform is doing. It takes an input signal, and let's call our input signal x of t. And x of t is that red line running around across time. And I can tell you the equation of this red line because we created it by ourselves. It is one of the blue line plus the other blue line called F1 and F2. So F1 and F2 was constructed by the summing of these two blue dashed line. And what do we really want to do? I mean, we want to find out how was xt constructed. And in this equation, I mean, we know that it's constructed by a cosine of amplitude 2 with a frequency of 2 pi 5. So omega equals to 2 pi 5. It means that it will have 5 cycles per second, 5 cycles of a cosine per second, and it is running across time t with a phase shift of minus pi over 4. So that is the first guy. So 2 pi 5. The other guy is 1 cosine 2 pi 10. Now, if you look at this blue dashed line, then you see, oh, the bigger one is the 2 cosine. And the smaller one is the 1 cosine. And the 1 cosine is faster rotating, or it is oscillating faster than the bigger one, because it is obvious from the equation. One of them has frequency 5 and the other one has frequency 10. Now, we know the original input. So what is the purpose of Fourier transform? It is actually just to find out what is the amplitude, what is the phase, and at what frequency did they exist. Exactly like what the equation is trying to tell us in terms of cosines and sines. So This picture is a picture of time here. What about this picture on the right-hand side? This picture is of time here. So observe that basically we just created a 2D graph and we rotate it a little bit, and now we are seeing a time here. Okay, I gotta mute you guys. Oh, how do I mute? Mute all. Right. So what we have is that we have time running across, and now these two little curve, I'm showing you the fat one and the smaller one, which is the fat dash ones and the smaller dash blue. So this guy is this guy. Oops. And the smaller one is this guy. So basically now I want to show it in 3D. This is still x of t over here, and this is time. And now I'm showing you only this blue dashed line across frequency axis. And I want to show you that, hey, I can now visualize the red line as a decomposition of these two blue lines. And along this axis, I can mark the frequency. One of them is 2 pi 5, the other guy is 2 pi 10, exactly as here in the bottom, 2 pi 5, 2 pi 10. And I want to capture the information very succinctly. And you realize that in the red line, when it's decomposed, there are only two components, one at 2 pi 5, one at 2 pi 10, with the amplitude of 2 and the amplitude of 1. So 2 and 1 are sitting here. The frequency is sitting there. And then all I need now is the phase shift. Minus pi is here, and plus pi is here. So I erase all these now. And you'll see that this is the other way I could have observed my time signal. And really, this is what Fourier transform is. It is simply, instead of observing the original signal in red across time, we are observing these two diagrams here. We are now observing the same signal in these two diagrams. And from these two diagrams, we can reconstruct this equation. So far, is this clear? I mean, if years later, when people ask you what is Fourier transform, then the a clever way to answer it is it decomposes a signal into a sum. See, we are summing all these guys of sinusoids. And when we say sum of sinusoids, then what do we need in the sinusoids? We need, of course, the frequency where the signal is existing, the amplitude where of the cosine or the sine at that frequency, as well as the phase. So this is Fourier transform. And what is DFT? You realize that this is, I'm going to show you DFT now. So let's remember x of t, and let's remember these two diagrams as x of omega. Later on, you realize that in the Fourier domain, x of omega become x of k, and x of t becomes x of n. Okay, so I repeat. I'm now going to introduce DFT. The input to the signal is no more x of t, is x of n. because we only have n samples. X of k, the k is representing the frequency here later on. All right. Any questions, guys? Any? Is clear? Right. Then I would suggest you also read this Duke, this Git.io, and yeah, you guys can Google it and you'll find it, and it's very nice. So everybody is writing about Fourier transform, and you can read about Fourier transform. Now, let's try. Okay, we have x of n, and x of n is a sequence, and this sequence have a few numbers. It has 1 here, and it has minus half, minus 1, and it has half. Across time 0, sorry, n, from 0, 1, 2, and 3. And we can label this sequence as a vector, 1, minus half, minus 1, and half. So x is a vector with 4 elements. So now we are going to see the whole problem as a DFT problem. So I can give you a signal. Instead of continuous time, I give you a discrete time signal. Basically, it means just a sequence of numbers. So now you think of this sequence of numbers as what time was, and now I just taking discrete samples of it. And if you really want to label it, this guy is small x of 0, small x of 1, small x of 2, and small x of 3. And we call this an endpoint. And n equals to 4 point signal or a vector. Now we are going to send this vector into a machine called a DFT machine. And out comes, if this is a small x, the usual notation is a big X on the right-hand side. So we know that there is a relationship. Here, the little n is across sample time. Okay, so we call it time index. K is across frequency. Later on, you realize. And K is equals to 0 to n minus 1. So you realize, hey, I'm sending a vector, 4 elements in. Out comes 4 elements. What is different is now this is a complex n. Here is a real n. So I'm sending a real vector in. Out comes a complex vector. And this is DFT. So I haven't shown you what it looks like yet, okay, in linear algebra way. In fact, I should just throw away this first. And I should now write the equation. And the equation simply is W small x. And now I'm going to make my notation consistent. So this small x is here, and this W is here. So we have been doing linear algebra, right? And so now let's write the note, write the information here. This guy is R4, a vector of 4 elements. This guy is a 4 by 4 complex matrix. Means that it is a matrix that all its element is complex numbers. This is a 4 by 1 complex vector. So run by me again the question. So if you want to generalize, then okay, let's generalize. This is n by n. This is n. And this is n. And in our example, because our input is 4 elements, so n is 4, and therefore this W is 4 by 4. Does that answer your question? I can't. Yes. All right. Okay. So there are many questions now, but let's wait, huh? Let's wait. So you think so if DFT is simply this, then we are given this X. So the only problem is this guy, right? That's it. Because once we are just given the signal n sample, then all we need is to construct W, and then all we need to do is W multiplied by X, we'll get capital X. So what is the magic right there? So the real answer is this. Okay, let's do the simple one first. 1. W is square, right? N by N. Its columns are orthogonal. Oh, that's nice. And W inverse exists, right? Because since its columns are orthogonal, it is full rank. Therefore, once I have done this problem, I can do this problem. W minus 1x is equals to W minus 1 Wx. Therefore, small little x is equals to W minus 1 big X. So if you're in the DFT world, we call this the top box, the DFT analysis, because we take the input from time and we represent it in the frequency domain, the big X. While here, this is the synthesis DFT or inverse DFT, IDFT. It's called the synthesis equation. Here, this is time. And here, the input is the frequency representation. And we are taking the frequency representation of the signal, sending it into W minus 1, transforming it back to time. So these two equations is DFT. Finish. All right. So where's the problem now, guys? The only problem now is we have to figure out what W is. How's that? How's this understanding of DFT so far? Is that okay? Any questions? Anybody? Okay. All right. So I'm going to give you a clear example. All right. And show you what it looks like. So again, it's this same example. The same values that I'm going to play with, and I'm going to show you the big X. So this is the DFT machine. This is the x vector, which is 1 minus half minus 1 and half. And out comes the big X. And then I'll give you the answer now. Okay. It is 0, 2 plus j, 0, 2 minus j. This is one representation of it. The other representation, of course, we prefer is the magnitude and phase. So here, the magnitude is 0, real is 0, therefore, and imaginary is 0, so it's 0 angle 0. So it's 0 angle 0 for these two elements. And 2 plus j, you can convert, is 2.23, angle 0.46. And this is nice. This is 2 plus j. This is the conjugate of 2 plus j. So the magnitude is the same, and minus 0.46 for the angle. You realize that the DFT coefficients, we call this, the DFT coefficients are complex value, and they always come in conjugate pair later on. All right, now if you're in MATLAB, what do you think I would type, guys? Let's try. I know you might not be able to see this. Okay, yeah, but let's try anyway. In MATLAB, DFT is equals to FFT, and the word FFT is fast Fourier transform. So I will write small x first. Small x is equals to 1, 0.1 minus half minus 1 and half transpose. So I have 1 minus half minus 1 and half. So this is small x. Big X is equals to FFTX. That's all. Yeah, in one line of code. So I will write for you. Small x is equals to 1 minus half minus 1 half. Transpose. Okay, guys? And big X is equals to FFT. Oops, sorry. FFT of the small x. And out pops the answer. Okay, let's see the answer. And he gives me in, what do you call it? He gives me as a vector 0 plus 0i, 2 plus 1i, 0 plus 0i, and 2 minus 1i. Okay, so he gave me in, what do you call that? In rectangular form. So remember, I like to see things in the polar form. See, how do I do this very quickly? So the trick is use the command absolute and angle. Okay, use these two commands, these two functions, and now let us play with this. So the absolute value of x, so this is ABS of x will give you my absolute value, and the angle of x, the big X, will give me the phase. Okay, absolute x, okay, and angle x. So I get whatever I want in only like 4 lines of MATLAB code. So at least now, after maybe 20 minutes, you know that I am basically sending a sequence of numbers representing as a vector into a function called FFT. And this FFT is a vector of n samples, spit out a complex vector of n samples. And then now we interpret the values, and the values are rectangular, which is not very nice to interpret. Instead, we convert it to magnitude and phase. Now, once we understand this, let's go back to the picture. Magnitude and phase. Okay, just remember that. Okay, let's erase all this rubbish. So what is xn? This is xn. Just imagine that I have 4 samples representing this. Of course, it's not. You can play up to 1,000, 10,000 samples. It doesn't matter. But now we just say xn is 4 samples. Maybe you can think of these 4 samples. One of them is here, one of them is here, one of them is here, one of them is here. For example, okay. Now, what is xk? Xk xk is some magnitude and some phase, right? There, the numbers here are the magnitudes. The numbers here are the phase. Then where is frequency? Frequency is k. Okay? So let's go and see. You realize that the output of FFT is a vector of k of n elements, and its position tell us the frequency. Okay? So let's go back. And here, this vector, oops, this vector, the big X, has all these 4 elements. Where is k, guys? I should erase this first. And now let's tell you where k is. K. This is k equals to 0, k equals to 1, k equals to 2, k equals to 3. So now I have the magnitude, I have the phase, and I have k. Then you say, what does k represent? K represents the frequency in this way. Omega, the angular frequency, is equals to 2 pi divided by the big N times k. So as when k equals to 0, omega is 0 radian per sample. When k equals to 1, 2 pi over n. K equals to 2, 4 pi over n. K equals to 3, 6 pi over n. So as we are going downwards in k, we are getting higher and higher frequency. Okay? So this is why, this is how we interpret the coefficients. Okay. So far, anything else? Is it clear? I mean, in these 2 slides, right, we really have, understand what is DFT from a very high perspective. We just know that it takes a sequence and it will convert it into another sequence, and this sequence is just magnitude and phase at different frequency. Not sure what terms to use. Very good. So where is Fourier, correct? I mean, I tell you the Fourier the whole day, right? And I said, where is Fourier? Come. So, so, so where is Fourier's genius? Here, W. He's the guy who says, I am not going to just use some random W. I will now tell you what W to use. And because of his W, we call this whole transformation. This is a transformation. This is a linear transformation. W times X is linear transformation. It's not even only a linear transformation. It's an orthogonal transformation because W times X can be inverted back. Invertible linear transformation. And in fact, you call this whole thing a change of basis. So now let us understand what is W. Okay. All right. So W. the Fourier basis. So he says, let us introduce a set of n orthogonal vectors belonging to Cn. And then this, so it looks like this. And each of these vector is Cn. And I have n of them. Let's call this k equals to 0, k equals to 1, until k equals to n minus 1. Okay, I still haven't filled up the elements yet. Huh? And then, but you think, hey, there's n columns, there is, and each column has n element, then you realize that this whole thing will make a matrix. And let me call this matrix WH first. You realize it's not W, it's WH, okay? Mm, what are the elements inside here? All right, so the genius of Fourier, so actually this figure tells you something. So in this figure, my input is no, not my input, sorry. Let me rephrase that. I am going to construct this blue line, this solid blue line, with small, with this big blue line here, solid blue line, this green line, red line, orange, pink, and cyan. So for each of these frequency, I'm going to give him the amplitude and the phase. And when I sum it up, it looks like a square. So this is the analysis part of the Fourier transform. Or synthesis, I should say, synthesis. I use sinusoids of varying frequencies and each frequency I give him the amplitude and the phase and ask him to sum it up. He gives me the blue thing. So the genius of Fourier is this, or he says that to construct any periodic functions, okay, we just need to use sinusoids. Now, once we understood this, then you'll be thinking, we are going to, each of these element or each of these column vectors is the entire, what do you call that? Entire cosine. So one of the element here is one point in this cosine. And the entire vector describes the cosine. So far, okay? Now, of course, let's remember ej theta is equals to cosine theta plus j sine theta. That's Euler's equation. E minus j theta equals to cosine theta minus j sine theta. So now if I plus, then I have 2 cosine theta. The imaginary part goes away. So ej theta plus E minus j theta is a cosine of amplitude 2. So in fact, you realize that sine and cosine are not the atomic functions that we are interested in. It is actually ej theta, ej theta. And we are going to exploit this. We know that we can construct any sine and cosine with this guy. So what do you think we are going to build here? We're going to build a function of a certain frequency, a function of a certain frequency, and so on. The frequency later on you'll realize is 2 pi n times k for different k's. So this is the frequency that we are interested in, is radian per sample. Now, I'm going to give you the equation and then we interpret, okay? First is that these column vectors has n elements. Therefore, if I expand this for you, I should be thinking of n going from 0 to n minus 1 here, right? Each of these element is from the n equals to 0 to n minus 1. So let's examine this vector. Let's talk about the k column. Each of this first element is e plus or minus plus j 2 pi over n. This is the k, and this is n equals to 0 for the first element. And as I come down, this element, this is some n element. This guy is e plus j 2 pi over big N k, whatever n is. I just use a blue first. I call this the blue n. So this is the index n. I have the green k here. This is the k column in this basis. So you realize that this one equation alone tells me how to build this matrix called WH. And it is simply E plus J 2 pi over N Kn. And here it is K equals to 0 to N minus 1. And in this way down is N equals to 0 to big N minus 1. Now, where is this in the lecture notes? Let me show you. WH, right? University of WH. There. This equation, WH, I have written down here, E plus J 2 pi over N Kn. You look at all these elements here. It is Ej 2 pi K over N Kn. And I'm showing you how K is running across the columns and how N is running across the row. Later on, you'll figure out there's a 1 over N sticking around there for normalization. But WH is this. Now, these columns are orthogonal. I'm not going to prove that. These columns are definitely independent. And if these columns are independent, therefore this whole matrix is invertible. And when they are orthogonal, then the inverse of this matrix is very easy. We simply transpose. So you realize that later on, I will show you that WH and W is simply a conjugate transpose. Here, WH, W equals to I. Can you explain how I get EJ2 pi N over N? Okay. All right. Now, I want you all to uh, look at this W matrix. 。 this W matrix, should I look at WH or W? Okay, let's do it W. Visualizing W as a rotating phasor. This W matrix, I mean, later on you realize that. Let me try to figure this out. What would be a good way to explain? Okay, let's still stick around here. The Fourier basis, let me not make a mistake, is WH. Huh? You must be very careful. And it is a vector that looks like this with this element. Now, I'm going to now expand on this guy again. Okay? For k equals to 1 and k equals to 0, which is the most interesting two guys. And then k equals to 2 if I have time. This is E j 2 pi over n. K equals to what? K equals to 0. So k is equals to 0. And here, now n is equals to 0. What about the second element? E j 2 pi over n. K is still equals to 0 because I'm still at the 0 column. And n equals to 1. And E j 2 pi over n. K still is 0, 0. N equals to 2. And then my last element, 2 pi over n. K equals to 0. N equals to 1. Now, so I'm drawing for you this first column, okay? And how would this first column look like? So remember of our Euler identity, E j theta equals to cosine theta plus j sine theta. So I can break. Oh, 3, sorry, yeah. Thank you. All right, so it's n equals 0, 1, 2, 3, 4. Big N equals to 4. Now, what is the amplitude of this complex phasor? They are all amplitude n equals to 1, right? So is then, in fact, I never like to write things in rectangular format because it's impossible to see. Instead, I prefer to write here as 1 angle theta, right, guys? 1 angle theta is for example, if theta is pi over 2, for example, then where is it? It is simply an amplitude 1. Here's the amplitude is 1, and the theta is pi over 2, right? So we like to write complex numbers in as phases with magnitude and phase. So of course, this is the real part of the z, and this is the imaginary part of z. So then, okay, let's draw these guys. This is trivial because k equals to 0. Whatever n is, it will be 0. So this is, of course, 1 angle 0. 1 angle 0, 1 angle 0, 1 angle 0. And what is 1 angle 0? So what is 1 angle 0, guys? It is simply there. 1 angle 0. So it is 1 along the real axis. 1, 1, 1, 1. So this first column, okay, this first column here is a number all ones. And let's see. Which one is it? The DFT. Here, this column. A number of, oh, sorry, here, this matrix. Okay, guys, don't be confused. It's this matrix, the WH matrix, all one. I'm now going to draw and interpret the second column. Okay. Once I have finished interpreting second and third, then you understand how to draw any W matrix. So this is for W equals to 0. W equals to 1. Remember that each of the elements is E plus J 2 pi over N Kn. N now is equals to 4, for example. K now is equals to 1. So this is the K equals to 1 column. Oh, sorry. I'm going to draw for you this column, okay? The second column of WH. So actually, it is the second column of WH. And the elements are E plus J 2 pi over N. K is now equals to 1 because we are drawing the K equals to 1 column. Little n equals to 0. Second guy, EJ 2 pi over N. K is still 1. N is now 1. Third guy, K is still 1. N is now 2. Fourth guy, 3. And then we are done. Now let's substitute n equals to 4 here in our example. 4. All the n becomes 4. And now let us draw, illustrate this in terms of its magnitude, which is all 1. Very nice. And now we just pick up the phase. 2 pi over 4 is pi over 2. But n is 0. So it's pi over 2 times 0 is 1 angle 0. Second guy, 2 pi over 4 is pi over 2 times 1. So this is pi over 2. This guy, now this is the interesting bit, okay, guys? From here to here, I am moving by pi over 2. From here to the next guy, I am moving by pi over 2 because I'm increasing by 1 step. So this is, depending on how you want to write it. You can write it as way, and then you are very sure what you are thinking about. What am I thinking about, guys? Why do I want to write it in this way? Pi over 2 times 0 times 1. You can see that this is n. N is the guy that is running along the columns for the K row. How does this guy look like? How? How did he look like, guys? So I'm not going to draw for you how he looks like. How do you draw 1 angle 0? If I give you a circle, and this circle is the real part of the complex number, and this is the imaginary, this is 1, this is minus 1, this is j, and this is minus j. Where is 1 angle 0? It means the magnitude is 1 and the phase is 0. So let's use a green guy. So this is the first element here. Second element, let's use a blue. 1 angle pi over 2 means 1 here, angle pi over 2, right? Third guy, green again. 1 angle pi. What is 1 angle pi? Here, pi. The magnitude is 1 angle pi. And the fourth guy, 1 angle 1.5 pi. Where's 1.5 pi? Here, in the bottom. So, so you now actually can see that I have a phasor that is rotating anti-clockwise, and it's going to move with the same magnitude, but each time it moves, it's moving by what? It is moving by pi over 2 radian per sample. Because whose sample? Time is sample. Every time I move by one sample, I'm moving anti-clockwise by pi over 2. And where did pi over 2 come from? It came from here. 2 pi over 4 times k. With different k's, I'm going to be faster and faster because 2 pi over n is fixed. All right, let me draw for you this phasor, okay, as a graph over here. It's going to look like this. This point pointing here, it means that I am having amplitude 1 and degree 0. How about this guy? I'm going to draw up because he is rotating 90 degrees anti-clockwise. What about the third one? I'm going to draw the same point here, the origin here, and the last guy here. So in these 4 elements, you see a complex phasor that is rotating anti-clockwise. After 4 samples, he will repeat himself, and so on and so forth. Clear, everybody? Okay, if you're clear, I will show you in MATLAB how we actually view this. So we have just drawn the second column of WH. Okay, let's okay. I'm going to draw this. I hope it runs. Oh, wrong guy. Okay, I'll show it to you later. Okay. Okay, let's run. Oops. Come on. All right. I'm drawing for you what I've just described using 2, 4, 6, 8, 8 by 8, n equals to 8. It's easier to observe. This is the first column of K. It is a phasor, like, I mean, uh, all ones. And all ones, the phasor would look like this. All ones. It is 1 amplitude angle phase 0. So you see, it's all 1. Okay, I'm going to change n equals to 4 for you first. Let's run. See? Here, n is going from 0, 1, 2, 3. Here, column is going from k equals 0, 1, 2, 3. I am plotting the complex phasor as magnitude and phase. Here, k equals to 1. Here, k equals to 2. Here, k equals to 3. Now at n equals to 4, it's very, very hard to observe what's happening here. So I'm going to make this now n equals to 8. Okay? So now I'm drawing an 8 by 8 matrix. This is interesting. K equals to 0, still nothing is happening because K equals to 0. 2 pi divided by n times 0 times whatever n is still 0. So 0 degrees means amplitude 1 with 0 degrees. K equals 1 is the most interesting example. You'll see that I have divided 2 pi divided by 8 now. 2 pi divided by 8 is pi over 4. That means as I'm moving across time, I'm moving by 45 degrees. Can you see? 45 degrees, 45 degrees, 45 degrees. And after 8 sample, I have reached almost, the next sample I will repeat. So it's 2 pi over n times k equals to 1 across different n. What about 2 pi over n? K equals to 2. As I'm moving across k, my rotating phasor is rotating faster. Can you see? Now, in one step, I make pi over 2. Just now, I make pi over 4. Now I make pi over 2. See? And if I keep on increasing, I am moving faster and faster. Now, this is a very important concept. Huh? I mean, once you understand this, I mean, you understand how to derive W again, right? All over again. So I'm now going to show you K equals to 16. Okay, go. Now, actually, a K equals to 16. This is a WH is a 16 by 16 matrix. You'll realize that, again, the first column is all ones. The second column start from 1, and now my phasor is rotating. See? Rotating, rotating, rotating. And after n sample, I'll reach back the same point again here. So this is the last sample before n sample. But you can see him rotating. And here, k equals to 2, he's rotating, what, 2 times faster than this. At k equals to 3, he's rotating 3 times faster than this. K equals to 4, 4 times faster than k equals to 1. So the take-home message is WH is a basis of orthogonal complex exponential rotating at different harmonics. That's WH. And Fourier says, once you have this, it's enough. You can reconstruct anything for, if you're in sampled time. How's that, guys? Okay? So wait, I will ask you all to comment. Okay, maybe I will stay. Okay. Any comments? Okay. Tell me, or I just didn't do anything useful for you guys. Oh, Malvin, you didn't understand anything. Oh, you don't understand. Oh, okay. Actually, mm. Malvin doesn't. Okay, you don't understand, but what the dog? Haven't watched it. You have. I mean, you have to watch the lectures before you come here. Okay. Is DFT tested? For sure. Everything is tested until, yeah. How is W orthogonal to each other? Yeah, I don't want to go there because you have to prove. Could you show a question using DFT? Ah, okay. All right. Where can we find DFT practice questions? Okay. First is for the quiz, for our quiz, as well as the exam, you need to be able to do our tutorial. Okay. Now I will show it how to practice. Okay. Thanks. Thanks for the feedback. All right. Now I'm going to show you what we're going to do, or at least what we need you to know. And in fact, this slide shows you almost everything. I mean, at least that's the most basic thing we need you to do. So I will explain these two questions. I explain the first question first. DFT. And now is my x is what? 2, 3 minus 1, 1. So this is my x. Okay. Let's do the simple guys, let's do the simple things first. Let's do the the type of quiz question you might be expecting. I given you an x and I ask you to find capital X. And capital X is W small x. And you have to figure out what W is by yourself. And you plug in your small x is 2, 3 minus 1, 1. This is small x. And you'll get the big X. So far, okay? So this is question 8A.3.3. And it is called the DFT analysis equation because it takes in small x in time and spit out big X in frequency. And then you fill up this matrix over here. So that's it. That's the question, right? You know how to fill up this matrix, everything is done. Uh, Now, is this clear so far? So some of you ask me, show us a question of Shahu asked, show me a question of using DFT. There, this is the question. I given you small x, I ask you to find big X. What we did the last 1 hour was to explain what the columns or the rows of W means. Actually, I only explained what the columns of WH means. Right, now, if you find difficulty, so what should you do? You should just open up MATLAB, which is your calculator, and just try it. Once you get MATLAB's answer, you then compare against yours. So how to do it is we write small x is equals to 2, 3 minus 1, 1 transpose, and then big X equals to FFT. FFT is fast Fourier transform of small x. So let's type, and we are expecting to get this number here. Okay, so let's do. And in fact, right, I would even do it in a single line. Okay, all right. FFT 2, 3 minus 1, 1 finish. And I prefer to see it in column. So it is 5 plus 0, 5 plus 0, 3 plus 2i, 3. Did I make a mistake? Minus 3. I think he made a mistake here, right? Ooh, did I make a mistake? Oh, I made a mistake. Sorry. My God. I made a mistake. Not him. Okay. 5, 3 minus 2i. Correct. Yeah. Okay. Minus 3 and 3 plus 2i. Okay. So you see that in one line, I use MATLAB to do. And the question by our classmates is, MATLAB cannot be used. Yes, we can't because you can't bring a computer in. And yeah, we're going to only give you 4 by 4, 8 by 8, 6 by 6 kind of matrices. So you can write everything down. Okay. Now, so that's we get the first question done, right? We know how to do analysis. How to do this is analysis. How to do synthesis, guys? 8a.3.3, the synthesis. What does synthesis means? It means, here, I'm going to write for you. This is the DFT. It will produce what, guys? Produce the big X, right? DFT. What will it produce? The small x. So what is this? This is WX. This guy, W minus 1, big X. Okay, that's the pattern. That's it. So let's see our problem. 5, 3 minus J2 minus 3. So in fact, it's exactly these values, right? So I'm sending this big X here, and I'm writing this W minus 1. Ah, so so now you see what is W minus 1. It is this guy. Okay? 1/4 times WH is W minus 1. So it is 1 over N WH big X. So there. 1N WH big X. So that's why we tell you that DFT is linear algebra, right? We are just simply multiplying the matrix by W for analysis. And for synthesis, we are multiplying by W minus 1. That's it. So you do matrix multiplication with W and small x to get big X. Huh? Wait, let me. So do you do matrix multiplication with W? No. Shahu, can you clarify your question, please? Better color code. This is small x. This is small x. This is small x. Where's the big X? This is big X. This is big X. And this is the big X. Clear? Shahu? So do you do matrix? Yes. Okay. Now, so why is linear when the Fourier transform has sign? Okay, wait. What is WH? I haven't, I told you what is W. What is WH? WH is conjugate transpose. Very good. Conjugate transpose of what? W. Okay, so I think now it's 9:40, 8:30. Any questions, guys? So I've done up to, you know, I've done these examples, which is the most important for you guys. Maybe at least something like this will come out for the quiz or things so that you have to at least be able to do some 4 by 4 matrices and compute one or the other, depending on the question. How do you get 1 over n? Oh, guys, you're going to make life difficult, but let's try. Here, this is the slide to show you why the n appears. First is W and WH. I mean, we began with WH. WH was that column vectors. And you have to prove that, or I prove that the column vectors are orthogonal. And when they're orthogonal, then WH times W equals to not the identity, because each element of W was 1. So you imagine 1 times the other guy, which is 1, will give you n. So this column dot product with the inner product with this column will get you 0 because they are orthogonal. But when you do it against himself, you will get n. That's why you have n. That's why the inverse is 1 over n times WH. Okay. Does that answer your question? Why is it a linear transformation? Why is it a linear transformation when what? When it has sign. Is it sign? You're talking about sign? Maha? Okay. All right. The sine and the cosine happens in this element e minus j 2 pi over n. But although there is a sign inside each of these elements, actually W is a what? Is a matrix of numbers. It is there's no sine and cosine. They are just numbers. It is a square matrix of constant values, and of course it's complex values, but it is just numbers. There's no sign. The Fourier transform function has sign, right? I don't understand, Mahav. Ah, okay. Maybe you will be thinking, yeah, I guess I understand what you're saying. How do you get from the DFT matrix and the small x to the final answer? Uh, how do you get from the DFT matrix? This is the DFT matrix, W, and the small x to the final answer. You're talking about this, Sahu? Yes. So you're asking me how to do this, Shahu? Yeah, but we are doing a 4 by 4 matrix. We can do it. I mean, you have, yeah, but okay, let's try, guys. 1, 1, 1, 1. Just for example, huh? I mean, I'm just doing other examples, okay? I'm not even doing this example. 1, 0, minus 1, 2. For example, just for example, how do we get y? Let's say a and b. And I given you some a and b. Then the clever way to do this, yeah, is this a. Okay, the clever way. And the reason why I want you to do matrix vector multiplication in this way is because you realize what? You realize that if I've given you a very complicated matrix, for example, 1, 1, 1, 1, and 1 angle something, 1 angle something, 1 angle something, 1 angle something, and then, you know what I mean, right? And then last one is the 4 by 4 matrix, whatever. And I only give you, for example, 0, 3, 0, 0. Please don't go and multiply everything out because this is this guy multiplying by this column is 3, 1, 1, 1, 1 angle, and then you go and fill up. And then you realize that this guy is plus E, J, is it minus or plus? I always get confused. 2 pi over n, k, n. Now, is it plus or minus? Depends on the question. Analysis or synthesis. Clear, Shahu? So for all x with the same number of samples, W is the same. So for all x with the same number, yes, correct. Initials, you're correct. I mean, we start from this picture, right, guys? W is an n by n matrix, and it depends on the n. So we always ask n point DFT. Is it 128, 4, 16? Of course, in the industry, we are playing with 256, 512 n. And then if you realize that, wow, you got 512 by 112 matrix, W is huge, right? That's why in the 1970s, people derived the fast Fourier transform, which is the exact implementation of the DFT transform in a fast manner. Okay? Anything else? Okay. So I'm going to spend the next couple of minutes answer any questions that you might have. And then actually on next Monday, I would do the tutorial question 5. The tutorials question number 5, which is where as a revision. Ah, maybe I should show you some MATLAB. Now I want to show you what this looks like. Okay. Now I wrote a code, and the code is basically plotting a complex exponential rotating. So I run this first and I'll explain. So we are seeing the same function in 3 different ways. In 2D, this is the real axis and this is the imaginary axis. In 3D, this is the real axis and on the top is the imaginary axis. And here coming out to us is time. And here, remember that every time we have e, j, theta, we are having cosine theta plus j sine theta. So this is the real part, and this is the imaginary part. So when theta equals to 0, cosine 0 is 1. 1 plus j 0, this point. What about this point? Same. Along this is real 1 plus j 0. And here is 1 plus j 0. So I'm going to rerun this and you observe the red line, red thing running around. It is running anti-clockwise. So I am moving things around by positive radian per sample. See? running, and he's rotating anti-clockwise in a fixed circle across time in a 3D plot. Now let's observe the 2D plot. He's running here anti-clockwise, pa, 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 completing one circle after n sample. He's periodic, he will hit at the same point. Okay, now I'm going to change for n equals to how many, guys? N equals to pi over 8. Pi over 4, maybe? Maybe 10 points is enough. Oops. Yeah. Maybe pi over 12. Yeah. So I'm plotting only 12 points. Can you see? And then at each step, how many? It's always 2 pi over n times k. That's, so you can understand what is this equation now, I hope. What is, I'm plotting this column vector, okay? This column vector. Each of these element is that red dot moving around. Okay, next question. Is Wx still a linear transformation? Yes. No problem at all. W can be a complex matrix. In fact, when you go for advanced linear algebra, W is complex. And yeah, no problem. W can be a complex valued matrix and you will still get a linear transformation. Any other questions, guys? Okay, maybe I'll pop this out and you guys can tell me what you really think. Books recommendation. Okay. Recommendation here, guys. In the references, 8A.3, he's the best guy, right? Brunton is one of the best guy I've ever seen teaching us. And then see, in one slide, that black picture there, he explains the whole of DFT. But he took 17 minutes. Yeah. So I'm doing it at a much slower pace than him. Okay, but I think he's very, very clear. So why don't you go and listen to him? That's one. Brunton, and there are many others. And that, in fact, I like to visualize and animate. So depending on you. And if you really just want examples of, 4 by 4, listen to this lady. I mean, she worked it out completely, right? Ken? And and then yeah, someone asked me how to prove orthogonality, right? Who's that? Let me find for you. Who asked for orthogonality of the columns? Anybody? Can someone tell me? Yeah, so this page in 8A.3 at page 28 is proving orthogonality. What else? Here explain H, the conjugate transpose. What does conjugate transpose means? Okay. So I leave the, the more additional stuff at the references so that you guys can do. But the take-home message is really you have to do this at least, and you have to understand all these W matrices that is running around like what we are doing for the last 1 hour. Anything else? Let me see the comments again. Can we use MATLAB in the finals? No. It's confusing. Yeah, it's not very easy, of course. What does harmonics mean? Oh, okay. All right. Harmonics. Harmonics. Oops. So if this guy is 1 second, This guy is still 1 second. How is xt1 related to x2t? How is their frequency? This frequency is what? 1 hertz, right? Because he's going at 1 cycle per second, right? And but what is the omega of f1 of this signal? What is omega, guys? Can you tell me, please? Anybody? In the chat. Please tell me. This is 1 hertz. Everybody know that. It's 2 pi. Because omega is 2 pi f1. 2 pi 1. 2 pi. And the unit is radian per second. It means that in 1 second, I am completing 360 degrees. 2 pi. Radian per second. What about this guy? This guy is f2. He is what? How many cycles per second? He's 2 hertz. He is 2 cycles per second. His unit is 2 pi 2. He is 4 pi radian per second. And how is x2 related to x1 in terms of harmonics? He is what? What's the word? Second harmonic. Yes. 2 times the first guy's frequency. Third harmonic. 3 times the first guy. There must be a first guy. Okay, if there's no first guy, then we say harmonic. Right? Harmonic with respect to who? So we must always give you the first guy. Now, therefore, you realize that our Fourier basis, basis, that vector that is running k equals to 1 is the most interesting one. The elements running from n equals to 0 to n minus 1 is rotating at what frequency, guys? At what frequency? Come on, guys. In n sample, he will make one complete round, right? Let's see our diagram again. Oh, sorry. I'm now showing you 16. I'm looking for k equals to 1. In k equals to 1, he's rotating, and after 16 sample, he will repeat. So the answer is omega equals to 2 pi over n. Here k equals to 1, radian per sample. So his frequency is this, 2 pi over n k1. I mean, whatever k is. This is the fundamental frequency of the basis. Then when k equals to 2, what happened? Who's changing? He's changing. 2 pi k equals to 2. Second harmonic. He's rotating 2 times faster than the first guy. K equals to 3, 3 times faster than the first guy. So we are talking about harmonics. So Fourier introduced the basis. The basis are complex exponentials of different harmonics. That's it. 2 pi over n, Jasmine, not 2 pi. 2 pi over n is the fundamental frequency of the first basis. Basis A, k equals to 1. Why is k equals to 1? Oh, okay. Where's my... It's not k equals to 1 only, adjustment. It is this column is k equals to 0. This column is k equals to 1. This column is k equals to 2 until k equals to n minus 1. I'm always interested in not k equals to 0 because k equals to 0 is not very exciting. Because when I dump k equals to 0, my whole complex exponential is ej 2 pi over n times 0, which is all 1. However, when I dump k equals to 1 in, then I get ej 2 pi over n times 1. 2 pi over n is radian per sample. Now n is changing. Therefore, I get a complex exponential rotating one round, one complete round after n sample. That's why k equals 1 is the most exciting one. Clear? Oh, cool. I hope I'm not boring you guys. Okay. Is the unit of frequency still 1 second here? Okay. Okay, this is a revision, guys. All right. Okay. This is in continuous time. Therefore, his unit is seconds, right? How many cycle per second? How many radian per second? Correct? Yes? Eben, did I pronounce your name correctly? Eben? Yes, Eben. Okay. All right. Now, what about this guy? I'm going to draw a complex exponential that is rotating. Okay, can you see me? This guy is x0, right? This guy is x1, yes? And so on, x2. So xn, what is the equation I should write? This is amplitude 1. 1 e j. What is this? I'm going to write here. What do you think I'll write here, guys? That little box. 2 pi. No. It is 2 pi over what? 2 pi over how many? 0, 1, 2, 3, 4, 5, 6, 7, right? 6, 5, 4, 3, 2. At the 8th sample, what do I get? I get back x0. So this is 2 pi over 8. Why? What's this? What's this guy? He is my frequency. He says that I will travel pi over 4 radian. And the unit is what? This guy is sample. Every time I'm moving by one sample, I am increasing my angle by pi over 4. See? Pi over 4. Every time I move by one sample, the amplitude is 1. Nothing changed. Your amplitude. Phase is changing by pi over 4. Pi over 4. Pi over 4. Pi over 4. So this is 1 ej 2 pi over 8 times n. K is 1. K is not here. So what is my frequency? What frequency is a bad word here. What is the correct term I should use when I'm showing you it is a rotating phasor? What is the correct word? No, angular frequency. Angular frequency. Right? I have an angular frequency of how many radian per what, guys? The unit is not time, sample. Right? Well, here in the previous example, It was radian per second because I am in time, continuous time. Now, now, guys, why do I draw a circle? Because you say I am drawing a circle because I am drawing a, a complex exponential rotating. Where is my cosine and sine? How do I view cosine and sine? Okay, let's see. Run, right? Uh, complex. Is it rotating? Let me find the correct video first. Please wait. Maybe this is enough. How do I get a sine from a rotating phasor? And here is the complex rotating phasor, and here is time. And now this blue thing is running across time, and here is running across time as well. You can think of it as time. That's why a complex phasor, when he rotate one round, he's making 2 pi. Okay, that's the key idea anyway. Clear, guys? Have you seen this happening? Okay. Let me see the. You have any more questions? Too many variables got lost. Mm. Actually, there's only about 5, 6 variables. Okay. What's the dog doing? Anything else? Okay, if not, we're done today. What I will advise you to do is revise quickly, go through the tutorial questions. On coming Monday, I would spend 1 hour doing this question. Where's my questions? I'll do question number 6. I will discuss this completely so that you can, I mean, yeah, we actually revise this again. Now we are interpreting and we are revising and we are doing this again. Question 5 is trivial, really, but if you really have a problem, we can do question 5. And this will be the type of quiz question that we are expecting, and it's only n equals to 4. And I can show you the solutions and oops. Yeah, I'll show it to you on Monday. How's that? Anything else, guys? If there's not, then we are going to quit now, and I'll see you again on Monday. Have a good weekend. Thank you. Thank you, everybody. Yeah, just type something for me. Nice visualization. Yeah, it's cool. Real world applications. Oh, real world applications. Hmm. so many, but not, yeah. Let's do a 4 by 4 first. That's real world. I mean, real world is 256 by 256, 512 by 512. That's real world. Half cook. Oh, okay. All right. Okay. MATLAB is not tested, guys. Yeah. Okay. All right. Then that's it. I will see you again on Monday. Thank you very much, everybody. Don't understand anything still. Oh, come on Monday. Right. Let's try it again. Thank you. Goodbye.